Welcome back to our series Physics Made Easy for 10th graders. Today, we're diving right back into the fascinating world of optics for the fourth time. So, get ready to discover more about the wonders of light and its properties. In this fourth of our series, Physics Made Easy for 10th graders, we continue with optics. In part 2 of the series, we raised a point regarding defining the refractive index. In part 2 of the series, we noticed that the refractive index appeared to have two definitions. The refractive index mu measures a medium's optical properties. It is defined as the ratio of the speed of light in vacuum to the speed of light in that medium. In part 1 of this series, we discussed why the speed depends on the medium. A ray of light bends as it crosses the boundary of one medium to another. The bending angle depends on the two media's relative optical properties. In this context, the refractive index mu is defined as sin I by sin r, where mu is the refractive index, I is the angle of incidence, and r is the angle of refraction. Let us see how the first definition leads to the second one. Before we proceed, let us understand the concept of the ray and wavefront. Light is an electromagnetic wave like radio, microwave, infrared, ultraviolet, X-rays or gamma rays. The electric and magnetic fields associated with the wave are confined to a plane perpendicular to its propagation direction. This direction of propagation is called the ray. The wavefront associated with parallel rays is a plane wavefront, while that associated with a divergent ray from a point source is a spherical wavefront. Geometrical optics uses the direction of rays to study certain light behaviors, for example, reflection and refraction. Geometrical optics cannot explain the phenomena of interference, diffraction, and polarization. To explain these, one must invoke the wave nature of light. This branch of optics is called wave optics. Here we restrict ourselves to geometrical optics while discussing refraction. This diagram shows the cross-section XW of the wavefront on the plane of the screen. The ray, which is perpendicular to the wavefront, is in the plane of the screen. The wavefront moves in vacuum with the speed c. Let us see what happens when the wavefront enters another medium, say glass, at an angle I. As the wavefront enters the glass, a section of the wavefront will be in glass and the rest will be in vacuum. These two sections will travel with different speeds. In the vacuum, light travels at a speed of c. Light travels slower in a medium like glass, denoted by v. As the wave proceeds, the section in glass progressively increases. As the speed in glass is less than in air, succeeding positions of wavefronts in glass are closely paced compared to the positions in vacuum, while the section in the vacuum decreases. At point y, the wavefront is totally in the glass. The direction of the original ray is along SO. Inside the glass, the wavefront Vy travels along the direction OT. The angle SON represents the angle of incidence, denoted by I. XW is perpendicular to SO. XY is perpendicular to OM. Hence, the angle WXY equals I. The angle MOT represents the angle of refraction denoted by R. XY is perpendicular to OM. VY is perpendicular to OT. Hence, the angle XYV equals R. Consider the triangle XWY. Sin I equals WY divided by XY. Consider the triangle XYV. Sin R equals XV divided by XY. Dividing the first equation by the second, we get sin I over sin R is equal to WY over XV. WY is the distance traveled by the portion of the wavefront at W in vacuum in time t. Hence, WY is equal to C times t. Similarly, XV is the distance traveled by the portion of the wavefront at X in glass in time t. Hence, XV is equal to V times t. Hence, sin I over sin R equals C over V. The bending of light traveling from one medium to another is due to the differences in the speed of light in the two media. The two definitions of mu are thus equivalent. It has been a wonderful experience sharing this series on optics from parts 1 to 4. The series aims to delve deep into selected topics to understand and create a passion for physics. Physics is challenging, but it need not be so if the basics are comprehended. The next series will be on topic heat.